When geological pressure builds up along the edges of the Earth's tectonic plates, it eventually tears the ground apart. In July 2026, a 7.3 magnitude offshore earthquake aggressively shook southern Mexico, prompting immediate tsunami warnings along the Pacific coast. Look at the sheer volume of debris filling the street. In Peru's Junin region, twin tremors measuring up to a 5.1 magnitude collapsed these adobe walls into thick piles of rubble, taking lives and destroying entire communities. And here are the thick gray plumes of a massive volcanic eruption. Halfway across the world in Indonesia, mountains like Semeru and Merapi are actively discharging accumulated energy through massive, miles-long pyroclastic flows. Mexico, Peru, and Indonesia are thousands of miles apart, but they share the exact same geological engine. They all sit on the Pacific Ring of Fire. This constant sequence of shattering earth and erupting rock is exactly how these highly active tectonic boundaries are supposed to behave. Then there is the Pacific Northwest of North America. Here, the Cascadia Subduction Zone stretches continuously for 600 miles from Canada all the way down to Northern California. This is a ghost forest. These dead stumps protruding from the foggy sand are physical evidence of the last time this specific fault moved. That was in the year 1700. For over 3 centuries, this massive coastal boundary has barely made a sound. A tectonic boundary this large remaining perfectly still for 300 years does not mean the region is safe. It means energy is trapped, and we need to figure out exactly what is happening miles beneath the ocean floor. A subduction zone is a boundary where 2 tectonic plates collide, and the heavier, denser oceanic plate is forced downward underneath the thicker continental landmass. Normally, plates slip past each other in smaller spasms, but at Cascadia, intense friction has completely locked the landmasses together. The oceanic plate keeps driving forward at 4 centimeters a year, compacting the rock and causing the edge of the continent to bulge upward. Year after year, that friction stores massive potential energy. When the plates finally overcome that grip and slip free, they will unleash a megathrust earthquake that could easily exceed a magnitude 9.0. To figure out exactly how tight that grip is, University of Washington researchers spent 13 years gathering data from offshore seismometers to stress test the fault. Because they can't drill miles into the crust, they measured sound. By tracking how fast ambient sound waves travel through subterranean rock, scientists determine its compaction. Tightly squeezed rock forces sound waves to move faster. On this thermal map, rock in the northern section is incredibly dense, meaning the plates are tightly locked. But in the central section, sound waves slowed down, showing less compaction. Here, perpendicular pathways allow trapped fluid to vent upward, periodically relieving pressure. Finding these active pressure release valves overturns the long-held assumption that the entire Cascadia Fault is operating under the exact same conditions. For decades, the dominant scientific fear was that when the friction lock finally broke, the resulting rupture would travel unimpeded down the entire 600 miles, tearing the entire coastline apart in one continuous event. Now, geologists recognize that these fluid channels and low-friction zones might act like geological circuit breakers. By releasing tension incrementally, these localized venting zones create a buffer. If a massive quake starts in the north, it could hit this lower pressure fluid zone and lose its momentum, restricting the destruction to a specific region instead of wiping out the entire coast. The scale of the coming disaster depends on these microscopic fluid dynamics. They are the difference between a localized crisis and a total coastal collapse. The rest of the Ring of Fire continues to remind us of its power, flattening buildings in Peru and throwing ash across the Indonesian sky. But beneath the quiet waters of the Pacific Northwest, a much larger, invisible machine is slowly grinding forward. Tracking the smoke and the rubble gives us a clear picture of the Earth's present. But if we want to predict and survive the next megathrust disaster, we have to learn how to listen to the silence.